Hi everyone, welcome back. Today we're going to do our final lesson for this week, and it is section 5.3 called Exponential Models. You're going to find your homework on page 90 of your workbooks, and I'm only asking you to do questions 2, 3, and 4. So questions 2 to 4. All right, let's get started. What is exponential data? So this is when you multiply or divide by the same amount to go from one number, so in this case a y value, to the next y value or to the next number. So right here you see a list of numbers. We have 3, 9, 27, 81. So basically, we're not adding by the same amount because obviously we only add 6 here, but then we add 18 here. So we're not adding by the same amount to get to the next number. But we know that 9 divided by 3 is 3, and that's the same amount as 27 divided by 9. So this number divided by that number, and 81 divided by 27, you see how they all give us 3? Because we're multiplying by 3 to go from this number to this number, and then again multiply by 3, and then again multiply by 3, that means this data is exponential. So that means that this data will grow very, very quickly because the next number is going to be 3 times bigger, and then the next number is going to be 3 times bigger. So when you have exponential data, it either grows or decreases. Another word for that is decays very quickly. And it also gives you a curve. Because we're not going up by the same amount, so on a graph, if we were going up by a constant amount, it would look like that. That would be linear. But in this case, it goes up slowly and then all of a sudden it swoops up. So this curve means it's exponential. So how do you tell whether data is exponential or not? So again, I set it up like I did the other lessons. So from an equation, what you're looking for is you're looking for the letter x as the exponent. So the independent variable, so in most cases x, is going to be what you see in the exponent section. So here we have y equals 2 to the power of x. So the 2 is the base and the x is floating in the air in the exponent location. That would mean that this is exponential. It could also look like something like this. Y equals 3, so the number in front is 3, and then 4 is the base, and the exponent on the base is x minus 2. And then we have a plus 1 at the end. So this x minus 2 that's up in the air, the x is up in the air, this would mean it's exponential. So these are two examples that would be yes. Over here, y equals x to the power 4 plus 1. This is not exponential. It has an exponent, but the letter x is not the exponent. So this would not count. If you are given a data table, so like before, we were doing first differences and second differences, the x's still have to be consistent and they still have to go in order. So -2, -1, 0, 1, 2, 2, 4, 6, 8, 10, 0, 3, 9, 6, 9, 12. It doesn't matter what the x's are, they just have to be consistent and you can't be skipping any. What we do is we still calculate our first differences. If they're not equal, we move on. We still calculate our second differences. If they're not equal, then we know it's not quadratic. What we then do is we calculate what are called our ratios. What you just saw me calculate up here, the 9 divided by 3, the 27 divided by 9. We calculate our ratios by dividing the lower number divided by the upper number, and we look to see if those are equal. If those are equal, then we know we have exponential data. So it's our ratios of our y values. So let's try it with these first tables. So again, feel free to pause, copy down what you need, get ahead of me if you like. So delta y, 1 minus 4 is -3. I'm not going to show my work just to save some room. 0 minus 1 is -1, 1 minus 0 is 1, and 4 minus 1 is 3. So that's my first differences. Based on that, this isn't a line. So this data is not linear. Then we go to our second differences, delta delta y. Now we find our differences of these. So -1 plus 3 is 2. 1 plus 1 is 2. 3 take away 1 is 2. All right, so we stop. This data is quadratic. We don't go any further because we've already proven that since the second differences are all equal, this data is quadratic. We don't test for anything else. It can't be more than one thing. Let's try the next situation. So again, the x's, do a quick check. -2, -1, 0, 1, 2. Good, they're all there. We have our y's, 0.25, 0.5, 1, 2, and 4. All right, so first column, first differences. 0.5 take away 0.25 is 0.25. So 50 cents minus a quarter is a quarter. 1 take away 0.5 is 0.5. 2 take away 1 is 1. And 4 take away 2 is 2. Okay, those don't match, so it's not linear. Let's try our second differences. 0.5 take away, again, a quarter is 0.25. 1 take away 0.5 is 0.5. And 2 take away 1 is 1. Those don't match, so it's not quadratic. So now this is where we find our ratios. So this, you add the extra column, and you have a choice. You can do your ratios of your delta y's, you can do your ratios of your first differences, or you can do your ratios of your y values. It doesn't matter, provided you did these right. So if I did my ratios of these, it would be 0.5 divided by 0.25. It would be 1 divided by 0.5. It's the number below divided by the number above. The number below divided by the number above. And we get 2. 50 cents divided by a quarter, 2. 1 divided by 50 cents is 2. They match. Therefore, this data is exponential. And since the numbers are going up, it's actually exponential growth. As we can see, the numbers are increasing quite quickly. If we had not done first and second differences, we could still divide 0.5 divided by 0.25 is 2. 1 divided by 0.5 is 2. 2 divided by 1 is 2. 4 divided by 2 is 2. So you still would have gotten the same answer for your ratios if you had just used the y values here instead of your second differences. So it doesn't matter which ones you choose to divide, but again, it's always the number below divided by the number above. The number below divided by the number above. So first and second differences are subtractions, ratios are division. All right, so that's how to tell whether data is exponential from a table. So next, how do you tell, and again, feel free to pause, from a graph, whether data is exponential or not? All right, so what do we got here? We have these two pictures. We have this case where I put time on the x-axis and amount of your savings on the y-axis. So these are dollars. And you see that the dots swoop up. So if the data swoops up or down, you know that it is exponential, or it could be exponential. So let's do a curve of best fit. There we go. So that would be an exponential increase. So that's exponential growth right there. I'll write that out. Exponential growth. And this is what you want your money to be doing in your savings account. You start off with a little bit, but then it builds on itself and it earns interest. And that interest then earns interest on itself. And everything keeps adding and adding and adding. And until it's grown to be quite a bit higher than what you originally started with. So again, this is your y-intercept, your original amount. But as time goes on and you let it sit there, you let it accumulate, it's going to grow and become quite a bit. In this case over here, we have time again in years on the x-axis, value of something. So in this case, I put value of a car in dollars. And we start up here, say at 25,000. But you notice then it swoops down like this. So if I was to do a curve of best fit, that's what it would look like. And you notice, again, that it doesn't look like a parabola. It's not a U shape, but it drops pretty drastically. So after the first year, your car's still worth quite a bit. But after the second year, it's dropped quite a bit from what it originally was. And then it drops even more, and then it drops even more. And it's always dropping. This is exponential decay. So decay for decrease. More specifically, if we're talking about the value of something, you might know the word depreciation. So things like cars and technology, they're never worth the same as what they originally were worth many years later. And this is what's happening to them. But notice it kind of levels out over here. It's never actually ever going to be worth $0. So we're never actually going to touch. This curve is never going to come down and touch the x-axis because it's never actually going to be worth nothing. It's always going to be worth something. Even if it's 0.000000001, it's still something. So that's why you see it kind of leveling out. It's getting closer and closer and closer to the x-axis, but it never actually touches the x-axis. So it's important to see that whether it's growth or decay, that the curve is increasing or decreasing, but it's not increasing by the same amount all the time through. So the curve does not have a constant slope or a consistent slope. Its steepness keeps changing. So we're not very steep here, and then we're a little bit steeper, but not that much, and then a little bit steeper, and then a little bit steeper, and then a lot steeper, and then super steep. Here we start off super steep, a little less steep, a little less steep, and then hardly steepness as we move forward. So because the slope is not consistent, it's always changing, that tells you that it's definitely not a line. All right, so hopefully that will help you on your way as you work on page 90, questions 2, 3, and 4. All right, let me know if you have any questions. Bye.